Okay, thank you very much for the invitation. This is a joint work with Elijah Bodish from MIT and Vasily Krylov from Harvard. It's work in progress, so any comments are welcome. And my talk will consist of two parts. The first part will contain no new results, and it will be about the Springer resolution and some geometric constructions associated to it, mostly due to Bezrukovnikov and collaborators. And then we'll try to do a similar thing with another resolution of singularities in geometric representation theory, resolution of affine Schubert variety in affine Grassmannian. So, okay, let's start with the first part with the Springer resolution. So, let G be a reductive group over complex numbers. And we'll consider the Springer resolution. So what it is, and tilde is the cotangent bundle to the flag variety, which can be described as the set of pairs B and E, where B is a Borel subalgebra inside G, and E is a nilpotent element inside B. And it can be mapped to the nilpotent cone, just nilpotent cone. So let me just write in the same fashion. It's the set of E in G, which are nilpotent. And the map is the obvious one. It just maps a pair B, E. Just forgets the B, it maps it to E. Okay, this is a resolution of singularities. And an important result associated with this resolution, starting point of our talk, is a theorem due to Kazhdan and Lustig. About the equivariant K-theory of the so-called Steinberg variety. So I take two copies of N tilde and take their product over the base, over the nilpotent cone. So let me precise that when I write, say, H covariant K-theory of a variety X, I mean just Grothendieck group of the category of coherent sheaves, coherent H equivariant sheaves on X. So the equivariant K-theory of this Steinberg variety, first of all, it has a natural algebra structure by convolution. If you take any square or any product of variety with itself over a base, you can convolve, you can take convolution of two coherent sheaves. And this algebra is nothing else but the affine Hecke algebra associated to the Langlands dual group. Affine, I will remind what it is. Affine Hecke algebra. And one can also take the equivariant K-theory of just the Springer variety of the cotangent bundle, and in these terms will be let me write it this way, it will be naturally a module over this algebra. So let me write what it is, then I'll explain that. So it's an induction from finite Hecke algebra to the affine Hecke algebra of the sign representation. Sign. It's also called the aspherical module. So, okay, let me now remind what this is. So, the affine Hecke algebra is an algebra which is generated by generators TW for any W inside the affine while group for G check. So here it's finite while group times the weight lattice for G. So just like that. With the following relations. So T W1 times TW2 is just TW1 W2 whenever the length in a affine while group of W1 W2 is the sum of length W1 plus W2. And also the quadratic relation or the Hecke relation for any simple S, we have this relation. For any S inside the set of affine simple reflections. So it's a deformation of the group algebra of the affine while group. For a affine while group, the first relation would be the same, and this would be just the square of this element should be 1. Okay. This is a very important algebra, and what's also important that it has a certain basis called the Kazhdan-Lusztig canonical basis. So I'll remind what is the Kazhdan-Lusztig canonical basis. There is an algebraic definition in terms of this affine Hecke algebra. I will give it. It is easy like to understand. It doesn't involve any deep notions, but from this definition, it will be completely non-obvious why one should consider such basis. Then I shall explain why it is important. So first, one can define the bar involution of the Hecke algebra. It is defined by the following rule. So Q bar is Q inverse, and TS bar is TS inverse. Sorry, no, TS inverse here. Okay, that's just some in the involution, and claim also of Kazhdan and Lusztig that there is a basis parameterized also by affine while group, basis in affine Hecke algebra, such that the following holds. First, it's self-dual for any W, and then the most important condition is that it can be expressed. So we have this basis T of TWs. It's called standard basis, and this CW is the canonical basis. And we require that they are connected by the following relation. Work over C. So yeah, we require that the transition matrix between these two bases is upper triangular, and also all the coefficient except for the diagonal one are divisible by Q. Yeah. Right. Yeah. So maybe I should say that it's also generate just a variable. Yeah. Thank you. Right. Just a variable. Yeah. And if we let Q equals 1, then we get this algebra. Okay. Yeah. So this is elementary definition, but it's completely not clear why one should consider such basis. Let me recall why it's important. Any questions up to this point? Yeah.
How's the lowest line and module over?
Yeah, it's just in the same way you define convolution here, you can define an action of any basically here, or can, yeah, just from convolution diagram here you cannot, you cannot like multiply two elements of such guy, but yeah, you can define an action in the pretty same way. Yeah. Oh yeah, and maybe after I gave the definition, let's again look at this definition of a spherical module. So we have a finite Hecke algebra, which is the same, but not for a fine Weyl group, but for finite Weyl group. So it's generated by TW for finite Weyl group with the same relations. It naturally lies inside the affine Hecke algebra. And for finite Hecke algebra, we have a sign representation, which is a deformation of the sign representations of the Weyl group. So TW acts by a sign of W. And then we can induce from these sign representations of finite Hecke algebra to the affine Hecke algebra. And that's what the equivariant K theory of N tilde. Okay. Well, maybe let me also stress out that the G action on this variety is the natural one. Just they both admit natural G action, and C star action is it contracts the nilpotent cone to zero, to a point, and it acts along cotangent fiber on the cotangent bundle of G mod B. Okay, and this C star actually precisely stands for this Q variable. Any other questions? Okay, so why this basis is important? It's for the following reason. So I'll be brief here. There is a lot to say about this whole Kazdan-Lustig business, but we have a category O, and we can consider its principal block. So principal block of category O, or affine Lie algebra. Everything is affine here. Actually, it's G dual because it's affine Hecke algebra for the Langlands dual. So it's a category of certain modules over affine Lie algebra, and it's since we consider this zeroth block, or any, I could take any integral weight, the Grothendieck group of this category has a basis of Verma modules, so W applied to zero. This is the shifted by rho action. These are Vermas. So that's why it can be identified with the group algebra of this affine Weyl group. But now we have from Hecke algebra, affine Hecke algebra, we have, as I said, the evaluation homomorphism to this group algebra, which just lets Q to 1. And one can check that under this evaluation homomorphism, if we let classes of Verma modules M W times 0 go to this, if we let these TWs in the definition of affine Hecke algebra be mapped to classes of Verma modules, then these elements of canonical basis will be mapped to the reducible quotients of these Vermas. So these are irreducibles. And this fact is the Kazdan-Lustig very famous and important Kazhdan-Lusztig conjectures, affine Kazhdan-Lusztig conjectures, proved by Bielenson, Bernstein, and Berlinski-Kashivara. So the point is that if you let Q equals 1, then these elements of canonical basis are precisely classes of simple modules in category O. And so knowing, for example, this decomposition of CWs in terms of TWs and letting Q equals 1, we know how to express simple modules via Verma modules. So it's an important basis, and there is a lot to say about that. But let me proceed. So any questions about Kazhdan-Lusztig conjectures? Or okay, so question, which is not easy to answer, how to see canonical basis CW from this coherent realization of Kazhdan and Lusztig. So we have some important basis in this algebra, and we have this important realization as equivalent K-theory of some variety. How so these elements should be are represented by classes of some sheaves or complexes of sheaves. So what are these sheaves? So the answer was given mostly by Bezrukavnikov and co-authors. Let me start with the following theorem of Bezrukavnikov. And Mirkovich. So there is a G times C star equivariant vector bundle E on this Springer resolution such that we consider the functor f maps to derived forms from E and tilde to f. This is a functor from the derived category of coherent sheaves on N tilde to the derived category of what I'll denote as A modules, where, sorry. And A here is the algebra of derived endomorphism of this bundle, but in fact there are no higher X. So it's going to be just like non-derived endomorphism. So this algebra naturally acts on any such shift. So it's in the functor here, and this is an equivalence. Okay, so the category of coherent sheaves on T star G mod B is just equivalent to the derived category of modules over some algebra. This equivalence is given by taking forms from some vector bundle. In this situation, in general, this vector bundle, or this more generally this object of the category, is called the tilting object. And this admits also an equivariant version, which is actually comes for free from knowing this. And yeah, we can consider equivariant A modules, G times C star. This is also an equivalence. Okay, So this algebra is called by Bezrukavnikov the non-commutative resolution, non-commutative Springer resolution, because it's the defining, because of this defining property, category over it's a non-commutative algebra, and model over it are equivalent to category of coherent sheaves. And here modules are finitely generated if we take coherent sheaves. And let me also point out that since we took the global endomorphism of some vector bundle on n tilde, it contains the algebra of functions, or basically the sections of structure sheaf on this tilde, the algebra of functions on the nilpotent cone, and this is a coherent algebra finitely generated as a module algebra over this center U of n tilde. Okay, so we knowing this theorem, we can. It's a very important structure on this category of coherent sheaves on Springer resolution. It is equivalent, direct equivalent to the category of modules or some non-commutative algebra. Now, how it helps to answer the question here? What are the modules over this algebra which give this Karzan-Lustig canonical basis? And the answer is given in terms the so-called perverse coherent sheaves. Let me give the definition. I will give it for this particular situation. I will consider F side-derived category of these equivariant A and tilde modules, G times C star, is perverse if again this algebra contains as a subalgebra the algebra of functions on the nilpotent cone, so I will consider it as a sheaf of algebras over this variety, and it's important. So I have a sheaf of algebras over this variety, and I consider sheaves of modules over this algebra, and I say that sheaf is perverse if for any G orbit on n, say O in n, let us consider the inclusion of the generic point of this orbit. Let's say generic point of O, this orbit. And I want the following two conditions to hold. First, the derived pullback, derived star pullback belongs to these homological degrees. And this will be a module over the local ring. The local ring of this algebra at this generic point. And I want this sheaf to be contained in these homological degrees. And second, I want the trig pullback of the same sheaf to be contained in the following. So above these degrees. So okay, this is the definition. Now, if there is a much mobile notion of perverse constructible sheaves, and they are defined as certain abelian subcategory inside the derived category of constructible sheaves, or sheaves with constructible homology. here it's the same, but you consider coherent sheaves. So these are called perverse coherent sheaves, or in this particular case, perverse coherent modules over this sheaf of algebras. And you have pretty much the same two conditions, that star pullbacks and Schrick pullbacks should lie below or above certain homological degrees. So this definition comes from this as a coherent counterpart of this constructible definition. And it turns out that in this case it works as well as the constructible definition. So it does define the reasonable object, but let me point out that for constructible sheaves you can take any reasonable stratification called Whitney stratification on any variety and define the perverse sheaves with respect to this stratification. With perverse coherent sheaves, it's not the case. It's actually essential to work with the covariant category. And it's essential that there are a finite number of g-orbits, and also it's essential that the dimensions of adjoint orbits, their dimensions differ at least by 2, which is the case for nilpotent cone. So in this pretty narrow class of situation, there is the notion of perverse coherent sheaves. But here it's okay. So it's a theorem of Bezrukavnikov that this category, let me say that perverse G times C star variant A and modules is an abelian Artinian category. So the most surprising part here is that it's Artinian. It's also Noetherian. So Noetherian plus Artinian means that any object has finite length. So there is an analog of Jordan-Holder theorem. And note that for usual abelian category of coherent sheaves, or equivariant coherent sheaves, or equivariant module over some coherent algebra, it's completely not true that this category is Artinian. You do not have finite filtrations of coherent sheaves. Yeah, but here it's surprisingly it is so. Yeah.
The option, but you can take the right category of equivariant modules. Equivariant, right?
You mean the difference between complexes with coherent cohomology and category?
No. Divide some like Ilya category of equivariant things instead of taking the equivariant derived category.
Oh yeah, but with coherent sheaves, I guess it's okay. Yeah. And for equivariant coherent sheaves over coherent algebra, it's also okay. So yeah. Yeah, so it's like that.
What's the like using some arbitrary stratification instead of like long time GH?
So it's not a theorem that there is no such T structure in this case if you take an arbitrary stratification, but just the proof doesn't work. If you try to prove that they define the T structure, then it doesn't work. So natural context, you should work with a stack with finitely many geometric points for proof to work. Here you take quotient stack by G action. If you have finite number of points, you have like stack with finite topological space. And it's also important that perversity function is monotone and comonotone. Here it's middle perversity. So it's okay. So yeah, and also one can again, similarly to the constructible case, one can describe what are the simple objects in this category. And they are IC extensions. So there is also coherent analog of IC extension of O V. So here O is again a G orbit. and V is a simple module over this algebra restricted to this orbit, sorry, to O module covariant. So basically you take a irreducible sheaf on G orbit module over this algebra, and then there is some canonical way to extend it to a sheaf, to complex of sheaves on the whole guy. It will be perverse. Just in constructible case, there is the notion of AC extension as well, and here it works. Okay. Nice. And finally, theorem also by Bezrukavnikov and Mirkovich, which answers the question which I posed, that classes of simple reverse A modules, well, let me say covariant A modules, form the Kazhdan-Lustig canonical basis in so I should put here covariant K theory of A modules, but now as I explained, this is just the same as a covariant K theory of until until the covariant K theory K group of coherent sheaves here. And this, as I explained, was the aspherical module. So I didn't mention that, but there is this, I defined the Kazhdan-Lustig basis in the affine Hecke algebra, and it's immediately to see from the definition of a spherical module. There are some classes of canonical basis vanish in the spherical modules, and other form also a basis of a spherical module, which is the Kazhdan-Lustig basis of a spherical modules. So so it's not a basis in Hecke algebra, but it's a basis in a spherical module. And yeah, in fact, the same construction works for the whole affine Hecke algebra. So for K theory of this guy, but then so I didn't explain that to stay in the realm of classical algebraic geometry. For this, it's actually essential to take the derived scheme, derived product of derived Steinberg variety over G, and coherent sheaves on that are equivalent to the bimodules, so modulus over A times M opposite. So derived tensor product of this algebra. And again, you should take simple perverse modules over this TG algebra on the important cone, and it will work out. But it's the same construction, just more technically involved. So that's why I explained it for the resolution. Okay, and finally, my final remark is that actually, final remark about this Springer resolution. Actually, all this stuff comes from an equivalence of Arkhipov-Bezrukavnikov between the derived category of coherent sheaves on the Springer resolution and the perverse. Now here it's actually to be the derived category of perverse Ivakhorov-Tekker sheaves on the affine flag variety of the Langlands dual group. So this is a local geometric Langlands style statement about equivalence of these derived equivalence of these categories, and here there is an abelian subcategory of just the with tautological T structure side. So this some Ivachori-Whittaker perverse sheaves here. I will not explain what this means. It will be not important for me, but it's some reasonable category here, and here you have the abelian subcategory of just perverse Ivachori-Whittaker sheaves on affine flag variety. So what is the corresponding abelian subcategory here corresponding to this T structure? And the answer is this perverse A modules. Yeah. And that's why classes of simples here correspond to classes of simples here in this Artinian heart of this Artinian T structure. Okay, but I'll not use that. I just wanted to emphasize that, like Bezrukovnikov, he never had a goal to describe Kazdan-Lustig basis. It just follows from his theory, his and his co-authors, about these coherent constructible equivalences of this sort. Okay, so I think that's it. That's all I wanted to say about this first part of my plan about Springer resolution and coherent construction of canonical basis there. If there are any questions on that, it's the time to ask. Yeah, so it means intersection homology, but it's also sometimes denoted like I shriek star. So it's some canonical way to extend a sheaf from an subscheme to the whole scheme. It's yeah, so it's just some right way to extend a simple objects on an G orbit here to the category of perverse sheaves. I will not explain that, but it's some construction. In constructible world, you can take just an image from canonical morphism from Schrick extension to star extension, but here you don't have. Well, here it's maybe a little bit more complicated, but it's still defined. Any other questions? Okay, then I'll proceed to the second part of the talk. Okay, so in the second part, I will deal with the affine Grassmannian for the group GLN. So it's fortunately type A only as of now. So the affine Grassmannian can be thought of as the quotient GLN of K mod GLN of O, where K is the field of Laurent series and O is the ring of Taylor series. And it is an int scheme, and the group, current group, I took the quotient by the right action of this subgroup. I still have the left action on this guy. So yeah, in the rest of the talk, I will not mention that it's GLN. I'll just write the affine Grassmannian group. And the orbits of this action are in correspondence with the dominant coveight. dominant co-weight. Oh, well, since I work with GLN, let me just say it's weights, but canonically it's co-weights. Okay. Yeah, and we'll denote lambda for the co-weight lambda. And now let me fix a sequence of fundamental co-weights. Let lambda be the sum of these fundamental co-weights. Then let me form the following variety called the convolution diagram. So yeah, here I will use the notation P for the canonical projection from G of K to the affine Grassmannian. And this convolution diagram is defined as follows. So what's written here, I take these fundamental Schubert varieties, I take their preimages in G of K, and then I multiply them over this current Lie algebra, Lie group. So it's some natural way to form a tower of these Schubert varieties. So it's a kind of twisted product of Schubert varieties corresponding to these omega I. So yeah, these guys are called fine Schubert varieties. I take fundamental Schubert varieties and consider a convolution of them. So if you've seen Bott-Samuelson varieties for finite flag variety or for affine flag variety, it doesn't matter. It's a construction of the same sort. It's just the Bott-Samuelson varieties for affine Grassmannian. And there is a natural morphism from here to the sum of these fundamental co-weights, and this map just maps point here. So an element G1 and G M to their product G1 dot GM. Okay. Any questions? It's just a way to form a twisted product of these Schubert varieties so that there would be a morphism to this guy. Okay, and there is also a resolution of singularities, a resolution of this affine Schubert variety in type A. Now, what's so good about this resolution? It's that again, here we have an action of G of O, so of an algebraic group on this variety, such that there is a finite number of orbits, and dimensions of all orbits have the same parity. So dimensions differ by 2 of adjacent orbits. Actually, I think it's the only 2 cases of resolutions of singularities which I know that have these properties, Springer resolution and this resolution of a fine Schubert variety, that there is this action which allows to define perverse coherent T structure here. And that is our goal. Our goal is to try to define the same T structure, the same classes of objects in the derived category here, and try to understand what kind of properties the corresponding basis has. Okay, but first I need to state in which terms we will describe this basis, and for that I have a theorem of Cauchy and Kamnitzer. Theorem will contain two parts. The first part is that there is an action of a fine quantum group UQ-GLM hat on the following thing: sum for K1, Km with fixed sum of Ki is equals to n, and I take the equivariant K theory with respect to this GLN MC star action on this guy, which I defined there. So, okay, that's the statement. It probably seems weird. We had the group GLN. We took a sum of covariant K theories of this resolution, so this convolutions diagram of M, convolution of M varieties, and for some reason we have an action of UQ-GLM hat. Let me explain why we actually should explain. I'll leave a place for the second statement of the theorem, but here I will explain why. So recall the so-called skew-Howe duality. So skew-Howe duality is a double centralizer type result of the following sort. It's happening on the following space. So let's take Cn tensor Cm and nth exterior power of this space. So here we of course have two commuting actions of GLN and GLM, and we can wonder like what's the double central wild duality type result, but on this space for two commuting actions of GLN and GLM. But let's wonder what is this space as GLN module. Then it's just the exterior power of Cn, the tautological representations M sum of itself. And now this is just by linear algebra, it's just the direct sum over the same summation, the summation over the same set of exterior powers of K1, Cn, tensor ... lambda Km, Cn. Okay, so hence on this space we should expect an action of GLM because it's isomorphic to this guy. But now how are these guys related? And so this is one thing, and the other thing is let's consider the non-equivariant K theory of this variety. Then one can show that in this case non-equivariant K theory of this variety is just isomorphic to the cohomology of this space, and also it's smooth, hence it's isomorphic to the intersection cohomology of the same space. And the intersection cohomology of this space are described by the geometric Satake equivalence. geometric Satake tells that this space should be identified with the product of representations of GLN of these weights, which can be realized as tensor product of this sort. Okay, so any questions about that? Okay, so if we would forget about the covariance, then this sum is by geometric Satake precisely can be identified with the representation of GLN of this sort, and by Skew-Howe duality, we indeed should expect an action of GLM on this space. But here we have this quantum deformation because of this C star, and also this deformation over this guy. So it actually turns out that it yields an action of affine quantum group on this space because of this additional covariance. Okay, and that's actually may seem strange why we should even construct such a thing, but Cauchy and Kamenetzer used it a lot. It's surprisingly powerful technique for studying this K-theory or stuff like that. They applied it for studying coherent categorification of knot invariance, and to the so-called K-theoretical Satake. In type A, they proved that using this action and many other things. Yeah, and so the second part is actually, it's not so deep, it's just explanation where this action comes from. And then it comes from homomorphism from these two, the sum of, like the tensor, the product of union of these varieties over the fine Grassmannian, which can be realized at sum of K1, K2, covariant K-theory, GLN. Yeah, so this actually should have been the other way around, but I wanted to explain why this action should exist first. So these homomorphisms yield the action here again by the same convolution procedure as before. So it gives an action, gives an action in part one. Okay, so I guess it's time to make a break, right? But please ask any questions.
The quantum group, even for, but it's still interesting even for Q equals 1, even the commutative one is interesting, or no?
Yes, it is. So it's not commutative, it will not be commutative, but yeah, if you, right. If you delete Q here and delete C star here, it still will be correct. Yeah. Mm-hmm. Okay, so right. Okay, now we are in a position to state our main theorem about this resolution. Okay, so first part is the following, that for any K bar or K underlined, this resolution admits a non-commutative resolution again. Let's call again what it means. It means here that there is a GLN of O times C star equivariant vector bundle that I'll denote E GR on this total space of the resolution such that the derived category of coherent GL and O times C star sheaves this resolution is equivalent to the again derived category of A GR modules, again with the same equivariance. So here now a difference with the previous situation is that then there this guy which we resolved was affine, so we spoke about tilting generators. Here it's projective, and we need the notion of relative tilting generator. It's not a big difference, but instead of algebra, we'll have a sheaf of algebras here. So there we also had a sheaf of algebras there, but it was the same as it was affine, so it was the same as algebra. Here we're going to have a sheaf of algebras here, such that modules over this sheaf of algebras are these are derived equivalent to coherent sheaves here. So here the equivalence will be given by let me denote this morphism by pi. Then it will be there. We took the global homomorphisms from E to our sheaf. Here we need to take like the inner sheaf, inner hom from E to F, and then take its like push forward here, or rather again everything derived. Yeah, so and it let me say that A GR is also the push forward. Well, here again we will not have higher acts, so I can write without derived everything, but yeah, it's derived in the morphisms of this sheaf. Okay, and the same statement for non-equivariant categories, but I will be interested in equivariant situations as well. Okay, so yeah, let me point out that this difference is called relative tilting generator. Very well. And the second point about the basis. So the basis of simple perverse modules over this algebra. Well, when I say modules, I mean equivariant modules, so objects of this category. I mean perverse subcategory of this category. So now this sum of K theories it is isomorphic. Well, yeah, we will not write that, but again, this K theory is isomorphic to the K group of these categories, so it indeed forms a basis. Is the global canonical, also called crystal basis for this action of quantum group. Okay, so maybe let me make a comment that it's old in the classical idea that one can use constructible, the usual perverse sheaves to define some canonical basis in some space. And again, it is a Noetherian Artinian category, so they form a basis in K group. Irreducible perverse sheaves form a basis. And for example, the basis in modules over quantum groups were defined by Lustig originally by this geometric construction involving perverse sheaves on some varieties related to quivers. And for Hecke algebra as well, they have this realization as classes of simple perverse sheaves on the constructible side. But here, one of the main points is that there are also coherent constructions of canonical bases. One can, in the category of coherent sheaves, there is a way to define also an Artinian T structure and a way to form to construct coherent categorifications of canonical bases, and that's also interesting, I believe. And particular, the basis for this quantum affine algebra in this module is indeed realized by this this construction here. Let me mention that the basis in the whole algebra, or at least part of this basis, also can be constructed in this guy. So for this homomorphism, elements of canonical global basis here. And in fact, for experts, let me mention that in fact, instead of this guy, one should consider the so-called Lustig's idempotent form of this algebra. So it will be an algebra without identity, but with a lot of idempotence. And it is this algebra that has canonical basis. But let me not go into that. In first approximation, you can think that it's just the quantum affine algebra. Okay, but I will speak about this, explain the construction of these for modules. Okay. Any questions? Okay. Yeah.
Crystal as a technical meaning, is it connected to the crystals in like for like Lie algebras?
Yeah. Yeah, those crystals. Yeah. So Lustig defined canonical basis for quantum groups with one geometric construction using perverse sheaves on some. Well, they are not quiver varieties in modern terms, but at that time he had some other varieties. These are not Nakajima quiver varieties, but other varieties constructed from quivers. And then Kashiwara gave a construction, this crystal which you mentioned, and there is a theorem that, well, up to some, they are, but essentially they're the same. Okay. Right. So let me explain how the proof works. If there are no other questions. By any chance, is there a new talk? No? Thank you. Thanks. Fancy one. Okay, so our main tool it's a modified Lustick's correspondence. And so that's an idea which goes back to Lustig, that in type A, the geometry of Fein-Grossmanian is related to the geometry of an nilpotent cone, so to the Springer resolution, which I spoke about before, and we will use that. So how it works. So we consider a partial flag variety for a different group, GLN plus n, mode parabolic corresponding to tau. So it is, I will define what it is, but it is some parabolic, so this should be some partial flag variety for this group, and this is the following flag variety. So it's the space of flags. So when these are flags in these are subspaces in this space, and when I write a number above inclusion, that means that the quotient has this dimension, so it's codimension of this sort. And remember that we fixed sum of ki's was equal to n, so we fixed it, and indeed here we have there sum plus n small, so we have this dimension. And in particular, we have the parabolic Springer resolution in this case, so we can consider the cotangent space, which we will denote by n tilde tau to the n tau. So this now is the closure of some nilpotent orbit. So we have a nilpotent orbit corresponding, so we have a homomorphism from this cotangent bundle to G. The image will be the closure of some nilpotent orbit. We denote it like that. And the claim about this construction is that there is a flat morphism of quotient stacks so given such a morphism, we can consider the pullback of coherent sheaves. So I'll denote by psi tilde functor from covariant coherent sheaves in the nilpotent cone, or until the tau to the coherent sheaves on this guy. Such that the following holds. So first of all, it's almost the K theories of these guys are related in the following way. So we can consider what this functor does on covariant K theories. And So here we have GLN plus N times C star. Now we can map it, restrict the shift to an open subscheme here. And it will be nothing else but C star, but the union of orbits which have less than or equal to n rows in the corresponding Young diagram of the corresponding nilpotent. So it may be too technical, but the fact is that this guy is a union of finite number of g orbits. If we restrict to some open subset of certain subsets of orbits, then it will become an isomorphism of covariant K theories. So two things which I want to say. First of all, the original construction of Lustig was without this additional n, just these numbers. And for this construction, this is not correct. There is no such isomorphism of K groups. But surprisingly enough, if you add this n, then that's why I wrote modified Lustig's correspondence. So it's because of this n, and then this property is always holds. So there is a part of this K theory, a quotient restriction to an open piece, such that after that it becomes an isomorphism of K theories. So the categories are different. Here we have a huge unipotent part because of this current part GLN of O. So the category is much more complicated in the sense that there are more X between objects there. But the K groups turn out to be the same. And so this was the first property of this psi. And the second property is also nice. The second property is as follows. So in both of these situations, there is finite number of orbits, and there are natural and very important slices to orbits. So let me say that this is star, and this is two stars. So psi is compatible with Mirkovich-Vybernov isomorphism. So what it means, we have this guy here, and there is a Slodovy variety. So in the nilpotent cone, there is a natural way to define a slice to one orbit inside the closure of the other. And if you take its pre-image under this resolution, you get a smooth variety in type A, which is called the Slodovy variety. So so this guy, yeah, inside this m tau, this slice to orbit O pi inside O tau, inside the closure of O tau. And on the other side, we also have a similar construction. There is a way to define the so-called transversal slices. And again, in this affine Schubert variety, you can define lambda mu slice to gr mu in gr lambda. And in type A, it's a remarkable result of Mirkovich-Viburnov in the spirit of this Lustig's construction, that these slices are just isomorphic as varieties, as Poisson varieties, the pre-images. And so what is our claim that psi is compatible with this isomorphism is that, let's say this is I. Oh yeah, and so I will not explain it just because I think it's enough concalities with this explicit construction, but yeah, there is again the way of this sort how to construct pi from mu. So they are in natural bijections here, and there is a way to construct, say, pi from mu or the other way around, such that these varieties will be isomorphic. And say this is I pi, this is j mu, and the claim here is that I can take a sheaf here, take its restriction to this slice, and the claim is that it's the same as I have is as if I would first apply psi here and then restrict it to this slice. And under this Mirkovich-Viburnov isomorphism, this is the same. Okay, so these are two main properties of this functor psi tilde, which I have. Let me mention that same for psi. So everything I wrote was without for resolutions for smooth varieties, but the same exists on the like for for singular varieties. There is the corresponding functors such that the same isomorphism exists, and the restrictions to slices themselves is also compatible with this under this Mirkovich-Viburnov isomorphism. Okay, so using these two facts about this Lustig's correspondence, we will be able to prove our main theorem, and the proof will be like using the results for using this Bezrukavnikov theory for Springer resolution. We can extract the facts about this Fine-Grossmanian resolutions using this functor. So let me now sketch proof of main theorem, part one. So part one was that there is a noncommutative resolution on this side. So the idea is obvious. Just take this this tilting generator on let me say on and tilde tau. So what I explained was for case of full flag variety, but Bezrukavnikov-Mirkovich actually do the parabolic case as well. So there still exists this noncommutative resolution there. And consider just this psi tilde of this vector bundle E and tilde. So this is a sheaf now on what I want. Now how to show that we claim that this is the required tilting generator. So I'll explain it in a partial case, but the full case is not much harder. So I will assume that lambda, my lambda lies in the dominant core-root lattice. Why it's good? Because then it's if in its core-root lattice, then in the corresponding connected component of the affine Grassmannian, there exists the GL of orbit, which is just a point, and the slice to this orbit, which is a point, will be an open subscheme. So then this slice W0 lambda slice to the 0 orbit is open in the whole guy. And from my second property of this Lustig's correspondence, what do we have? So psi tilde of this E and tau restricted to this open part this is because of our properties, the same as we would have first restricted to n so well, this psi is psi for restriction, so it's this the correct notion would be like psi also restricted to this, so it's just restriction along this isomorphism, and this is a tilting generator. So this also follows from Rukavnikov-Mirkovich. They show not only that the vector bundle on the whole n tilde is a tilting generator, but its restriction to any Slodov slice, to any Slodov variety, is also a tilting generator for the Slodov slice. But now, so we know that we have an equivariant bundle on the whole guy, and we know that its restriction to some open is a tilting generator. But now, property of being relative tilting generator is local over base. So if we have a resolution or any morphism, and we know that on the base of this morphism there is an open cover such that the restriction is a tilting generator, then it is a tilting generator on the whole. It's really it's an easier exercise on the like homological properties of an object which are required to be a tilting generator. And we have an open of very specific kind, but we have a GLN of O equivariance on the whole variety, and this slice it's not equivariant. So we can spread this open by using this loop group action. So using GLN O equivariance, we get the claim. So the open cover would be G times lambda mu for G inside GLN of O. This defines an open cover of the base. And of course, if we know that this open over this open, this was a tilting, and there is a global action of GLN of O, this for any G, it also will be a tilting generator there, and that gives us a cover over which we know that it's a base. So it's a short and, at least in my opinion, interesting proof. We get something very non-trivial about this derived category of coherent sheaves on this resolution of affine Schubert variety. It's equivalent to some category of sheaves over some algebra by this Lustig's correspondence in restriction to this cover by slices to 0. So okay, this is the sketch of the proof of the first part. Now this construction doesn't only tell us that there is a tilting, but it also tells us that this psi is compatible with perverse basis. So we constructed this algebra, constructed this tilting by using psi. So, and particular, if we take the algebra, the non-commutative resolution, so let me write that. This also tells us that this GL n plus n so as I explained, there was a surjection to this GL n MC star on this guy, and we know that this is compatible with the perverse basis. Again, because this is induced by this functor psi tilde. And we know that tilting here is mapped to tilting here by this map. In particular, the corresponding sheaf of algebras also is mapped here. So, and this is all compatible with filtration by orbits. And one can show, I skip all the details, but one can show that this functor is it preserves these perverse T structures and maps simple objects to simple objects. So this is there is something to prove here, but this construction tells us that it is compatible with perverse basis. In particular, we get some description of perverse basis here. So we have as of now, we have a description of the required basis here as an image of canonical basis here. So here our basis, which we want to describe. And here it's again, I haven't explained it, but there is a parabolic version of Kazhdan-Lustig basis. And so this is Kazhdan-Lustig, parabolic version of Kazhdan-Lustig basis here. Okay, and so maybe not to go into details, let me just sketch that there is an object which appears from Schur-Weil duality, in this case quantum affine Schur-Weil duality, called the Schur algebra. Okay, maybe let me define it properly. So we have quantum affine Schur algebra. So how it's defined, noted like this, as n plus n m. So it's defined as endomorphism over affine Hecke algebra of size, for GLN of size n plus n, of sum over parabolics of h hat so n plus n of CP, and CP here is a certain idempotent in the affine Hecke algebra corresponding to this parabolic. So it's W inside the affine group for this parabolic of TW, and that's an idempotent. And the claim is that there exists also homomorphism from this algebra to here, a surjective homomorphism actually. And here the sum runs over parabolic, which are just parabolic for GLM are just partitions. So L1, LM, sum of LI's equals to to n plus n. And let me explain so why this Hecke algebra constructed from Hecke side has a surjection from quantum affine GLM, and that just comes from Schur-Weil duality or basically this V omega 1, let's say TT inverse times M. So this is the natural module of a quantum loop group for GL M, and we take its n plus n tensor power, and we have a quantum affine Schur-Weil duality on this space with commuting actions of affine Hecke algebra and quantum affine GLM, and the common algebra on which it acts is precisely this, and this is called the Schur algebra. Yes, it also exists for non-quantum and non-affine cases as well, and there is a theorem of Schiffmann and Vassero that Kazhdan-Lustig basis in Schur algebra coincides with the image of canonical basis for UQGLM. Yeah. So this is a purely algebraic result. They did it by analyzing the corresponding crystals. So we have an algebra which naturally appears on one hand side from this Hecke story, and on the other side from this quantum affine story. And it's an algebraic result of Schiffmann and Vassero. It was actually, before it was a conjecture by Lustig, that this rejection is compatible with the canonical basis. So canonical basis here goes either to 0 to canonical basis here. And now using this, we can, how our proof goes, we know that our psi is compatible with basis. So we have description basis here as an image here. And we also know that this algebra, which actually can be identified with Schur algebra here, that's precisely the basis of this in this Schur algebra, also comes from canonical basis in quantum affine group. So using this, we indeed get a description of our basis as a canonical basis for quantum loop group. So we have a geometric construction which guarantees that our basis comes from this Schur algebra, so from Hecke story and Kazhdan-Lusztig basis here. And we have a purely algebraic result which tells that basis which comes from such a construction is actually the canonical basis for this affine algebra. So maybe I don't have time for all the details, but the proof goes like that, using this result. So okay, maybe that's all I wanted to say about this part of the story. If there are any questions, then please ask. Yeah.
In the Springer case, like what this tilting object is.
It's actually hard to construct it. So for SL2, there is an explicit description. You just take on P1, you take O plus O of -1, pull it back to the cotangent bundle, and that's the vector bundle. But it's the only, well, even for SL3, it's not pulled back from flag variety. So the construction goes through quantization in positive characteristic, then they lift to characteristic 0. So there is no explicit description, and it is a non-obvious construction. It's also not uniquely defined. Depends on characteristic, for example, to which you do a reduction. Yeah, so it's completely not there. There is no explicit construction a way of SL2. Any other questions? Well, I guess, I mean, I have 2 minutes. Maybe it's a good idea to stop here and place. Thank you.